Hello everyone, welcome to the last part of the presentation on areas of surfaces of revolution. After hard work, we are finally ready to prove the surprising theorem by Archimedes. I will explain why I use the adjective surprising in a moment. The main part of the theorem is the formula for the surface of the sphere. Let's see how this formula follows from the general result we derived in the previous section. If you recall, we showed that the area of the surface obtained by rotating the graph of a function is given by this distinctive integral in the red box. The only requirement on function f for this formula to work is that function f has a continuous derivative in the interval from a to b. Hence, in order to apply the integral formula we derived last time to the sphere, we need to find a function whose surface of revolution is equal to the sphere. Let's look at the image on the right. Clearly, we obtain a sphere when we rotate a half circle around its diameter, like we can see it here. Hence, we need to find a function whose graph is a half circle with radius r. Why don't we start with a whole circle? As everyone knows, the circle centered at point 0, 0 and having radius r is the set of points on the coordinate plane which satisfy this first red equation. X squared plus y squared equals r squared. Why don't we solve this equation for y? But let's notice that it is a quadratic equation in y, hence we should expect two solutions. So, moving x squared to the right side of the equation and then applying square root, we extract two solutions. One with plus sign, the other with minus sign. The two solutions naturally represent two half circles which comprise our circle. In particular, we can say that our circle is the union of the set of points xy which satisfy the equation with the plus sign, and those points represent the upper half circle, and the set of points which satisfy this equation with the minus sign, and they represent the lower half circle. So we see therefore that the function we were looking for, whose graph is half circle, is given by this blue formula. Square root of r squared minus x squared. And that function is defined in the interval from minus r to r. Now, since our integral formula calls for evaluating f prime of x, let's calculate that derivative here. So f prime of x is, of course, the derivative of our square root of r squared minus x squared, and this is a composite function. It is composed of the function square root of u, where u is r squared minus x squared. We will use therefore the chain rule, and the derivative of square root of u is 1 over minus 1 over 2 times square root of u, with u being this expression, and the derivative of u, which is this quadratic function, is simply minus 2x. When we multiply these two factors, we get this nice fraction. So the derivative of our function is defined again in the interval from minus r to r, and it is a continuous function on that interval because it is a ratio of continuous functions. Well, that means that we can apply our integral formula to the sphere, with the function f being given by this blue expression. The area of a sphere is equal to 2 pi times this specific integral. We know what f of x is, and we know what f prime of x is. So let's plug in the formulas we have for those functions. So here is our f of x, and here is the derivative we have just calculated. When we combine these two square roots and multiply out what's underneath, we obtain an expression where a lot of cancellations occur. So we have r squared minus x squared cancels this copy of r squared minus x squared, and these two red x squares cancel as well. So we are left with square root of r squared, which is simply r, as we see here. Now, we are integrating with respect to x, of course, so r is just a constant. We can take it out in front of the integration sign. So we are left with even a simpler integral, namely the integral of function 1. Now, taking antiderivative of 1, which is x, and evaluating that antiderivative at the limits of the integral, we get 2r. So, lo and behold, after all this maneuvering, we are finally arriving at the venerable formula for the surface area of a sphere, and that's 4 pi r squared. So we are just a step away from Archimedes' theorem. In order to motivate why that theorem is remarkable, let me reposition our circle so that it is oriented vertically. So let's enclose the half circle in a rectangle whose longer sides have length 2r, like here, and the shorter sides length r. Compare the length of the half circumference, marked here in red of course, with the length of the diameter, marked here in blue. So half of circumference is pi r, which is approximately 3.14 r, while the length of the blue line segment is simply 2r, the length of the diameter. So we have 3.14 r versus 2r. Now, let's rotate first the red arc. We obtain, of course, the surface of a sphere, and we know that the area of that surface is 4 pi r squared. Let's do the same with the blue line segment and rotate it around the circle's diameter. We obtain a cylinder which tightly houses our sphere, and whose area is given by this formula which we have derived in the first section of our lecture. So it is 2 pi times h times r, but we know that h is equal to the diameter, which is 2r. So again, we are receiving, surprisingly, 4 pi r squared. The cylinder's lateral area, excluding the bases of course, is the same as the area of the sphere. Now this is surprising because you would have never guessed that looking at our original picture here. Originally, we had the red arc, which is much longer than the blue line segment, yet rotate these two curves around the black diameter and you are going to obtain surfaces with the same area. Is somebody twisting space when we transition from 2 to 3 dimensions? One can only imagine Archimedes' ingenuity, who 2,000 years ago derived these formulas without the benefit of derivatives or integrals. And even with the benefit of those notions, it was quite a mouthful to arrive at this result. Thank you for listening.